Hello, everybody. We have been taking into account a range of problems based on variational principle, and in this video, I'll be actually executing this variational principle on a complicated problem like an harmonic oscillator. And this variational principle is, as we understand, is a powerful tool that's used in quantum mechanics to approximate the ground state of systems where we know that the exact solutions are very difficult. So for the anharmonic oscillator, the potential deviates. It deviates purely. It deviates basically from purity. Purity, I mean, from quadratic form to the harmonic, from the quadratic form of this harmonic oscillator, and making the problem much more complicated because we have the kinetic energy term, we have the potential energy term, and there's a deviation in that quadratic term. Now, what approach we would like to execute here is the general approach as we have used in case of hydrogen atom, in case of the harmonic oscillator. So the problem can be set up in the same way, like we have the general Hamiltonian for this anharmonic oscillator as H is say p square by 2m, then 1/2 of m omega square x square, and assuming the third term to be like lambda x raised to power 4. So this is our Hamiltonian. And the first term, as we all understand, it represents the kinetic energy. The second term, it represents the harmonic potential, and it's quadratic in nature. And then we have the third term here that we have introduced. The third term is lambda x raised to power 4, and this is what introduces this anharmonicity and harmonicity to the system. Now the challenge is here basically the presence of this x to the power of 4 term, and which makes Schrödinger equation unsolvable. It's practically unsolvable analytically, and this is where the variational principle comes in action. It becomes useful. So as usual, what we do is we use the trial wave function. So we have a trial wave. We choose a trial wave function, and the key to using this variational principle is selecting a good trial wave function, and which is our psi trial, if I say psi trial of x. And this function that we choose, it should resemble the exact wave function of the system, and it should also obey some good bounding conditions like going to 0 as x tends to infinity. Now, for the anharmonic oscillator, a good trial wave function is often chosen to resemble the ground state of the harmonic oscillator with a parameter that's varied as. So the very trial function, if I say psi of x, is a e to the power of minus alpha x square, that we have been using in the last two cases as well. But this alpha is a variational parameter that controls the width of the wave function in this case, and a is a normalization constant, and what it ensures is that the integral from minus infinity to infinity psi of x, which is a trial wave function, whole square dx is equal to 1. And what we do here is we apply the variational principle. And the variational principle states, what it states is that the expectation value of the Hamiltonian calculated with the trial wave function provides the upper bound to the true ground state, closeness to the true ground state, and this E trial comes out to be, so this is the expectation of psi, and then h, this is psi of x, then h, and then psi of x. Okay, divide by psi of x and psi of x. And as the wave function chosen is normalized, so we can take off this denominator, and we can write down this E trial as the expectation of the Hamiltonian, psi of x, then h, then psi of x. Now, to find this expectation value, what we do basically is we calculate this E trial. So what we do, we calculate this this expectation value as integral minus infinity to infinity, okay, psi star and psi star of x, then you have the Hamiltonian, and then you have psi of x, then we have t of x. This is whole divided by integral minus infinity to infinity psi of x whole square t of x. Now this expression, what happens to it? It simplifies to what? E trial. Should I call it T? Okay, let me put a T here. So E trial, with respect to that alpha that's to be calculated, is the expectation of the kinetic energy plus expectation of the V harmonic, and then the expectation of V anharmonic part. So this is how our energy is simplified to, and this is the kinetic energy term, this is the potential energy term, and the third one is the potential energy term due to the contributions in anharmonicity. Now what we do then, as we did in the previous case, we calculate this expectation value of kinetic energy, and exactly we do it in the same way, like minus infinity to infinity, then you have psi star of x, and then you have minus h cross square by 2m d2 by dx2, and then you have psi of x, then dx. And we have the trial wave function. What's that? That's psi is a e to the power of minus alpha x squared. And we have done in the previous video, we have calculated this a, and we have calculated this alpha, and the things boil down to what we have obtained is that this expectation value of kinetic energy comes out to be h cross square alpha by 2m. All right, and this on evaluating that integral, what we finally find is h bar square alpha by 2m. Now we have the next term, that is the V harmonic, and this V harmonic, it has to be evaluated in the same fashion, minus infinity to infinity psi star of x, then we will have 1/2 of m omega square x square. And we have done it in the previous case, psi of x d of x. And what is the result of this integral? This V harmonic, it comes out to be m omega square by 4 alpha. So this is our expectation value due to the harmonic term. This is our expectation value due to the kinetic energy operator. Okay, operator, and this is due to V harmonic operator. And then we have the next thing is the anharmonic potential. So for V anharmonic, what we have to do the same thing, minus infinity to infinity, then psi star of x, and then we will have lambda x to the power of 4, and then psi of x d of x. And on evaluating this integral and making those calculations, what we obtain here is we obtain this V harmonic is it is 3 lambda by 4 alpha squared. So this is your anharmonic term. So now we can write down the total energy expression, and we can write down that total energy expression as total energy. So what will be that we combine all the terms to get the total energy of the function in terms of alpha. So what is that? That is E in terms of alpha is it is h cross square alpha by 2m, and this is the first term, and then plus I have m omega square by 4 alpha, yeah, m omega square by 4 alpha, and the third term is 3 due to anharmonic term is 3 by 4 alpha square. Now these are our terms. Now from this equation, what we have to do is we have to calculate this alpha, and how we calculate it, we minimize this equation. And how do we minimize it? We minimize the trial energy that's coming over here, so that this dE of alpha by d alpha is equal to 0. So to do that, what we do is we take the derivative. So I would like to take the derivative of this equation. Okay, so I will take the derivative. So taking derivative. So what I'll have dE alpha by d alpha will be equal to, okay, what it will be? It will be d by d alpha of this h bar square alpha by 2m plus d by d alpha of m omega square by 4 alpha, then plus d by d alpha of 3 lambda by 4 alpha square. So this is what we do, and we individually calculate the derivative of this, the derivative of this with respect to alpha, and the derivative of this, derivative of this, derivative of this, and derivative of this. So we can easily see here the derivative of this will be h cross square by 2m with respect to alpha. So I can think of, I would like to write it in independent. So d by d alpha of h cross square alpha by 2m will be simply h cross square by 2m. Now the second thing is d by d alpha of m omega square by 4 alpha. So we have evaluated this differentiation in the previous video, and what it will come as minus 1 by 4 m omega square by alpha square. And we have the third term here, d by d alpha of, this is 3 lambda by 4 alpha square. And this will give me minus 3 lambda. Okay, minus 3 lambda, because this 3 will come, because when we'll take this alpha square up, it will become alpha raised power minus 2 when we'll take its derivative. So it is, what is it, 4. Okay, so when I'll take its derivative, the 2 will come down, and that 2 will cancel this 4 and will make it 2, and you will have minus 2 minus 1. Minus 2 minus 1 will give you minus 3. Then this alpha will come back to the denominator, and you will have alpha cube here. And so we have these 3 derivatives, and we have to set them all equal to 0. We have to add them in accordance with this equation and equalize this to 0 in order to calculate alpha. So what does that mean? That means h bar square by 2m, and then minus 1 by 4m omega square by alpha square minus 3 lambda by 2 alpha cube is equal to 0. All right, now in order to solve this, we can multiply this equation both sides by 4 alpha square. So multiplying both sides by 4 alpha square. So what we'll get here is 4 alpha square to eliminate the denominator. So multiplying this whole equation with 4 alpha square will give us what? So what we'll get, you can check it, we will get 2h bar square alpha cube minus m omega square alpha minus 6 lambda is equal to 0. This is what we will obtain. You can check it, and this is a cubic equation. You can see it's a cubic equation in terms of alpha, and which may not have a simple analytical solution, but at the same time this equation can be solved numerically for the specific values of for that we must have the value of h, we must have the value of m, we must have the value of omega, and we must have the value of lambda. All right, so if we have those values, only then this equation can be solved depending on the situation, and using the values of these constants will take us to the result to obtain the value of alpha for this particular problem that's under consideration. So this equation has yielded the optimal value of alpha by solving this cubic equation, and this equation can be numerically solved, and provided you incorporate the values of those constants that are provoked here. Now the optimized value of alpha, whatever the optimized value of alpha will obtain from here, is substituted back into the trial energy function, okay, to give the variational estimate of the ground state energy. That's the purpose basically, and this energy E trial is basically an approximation of the true ground state of the anharmonic oscillator. So by choosing more sophisticated trial wave functions, you can improvise the accuracy of the result for the particular problem. So to conclude this this video, a quick reminder is that using variational principle of the anharmonic oscillator involves choosing an appropriate wave function, calculating the expectation values, minimizing energy with respect to the variational parameter, and then this method provides the powerful way to estimate the energy of the system where the exact solutions are not possible. So with this, I would like to end this conversation. So because depending on all those parameters, you will have alpha, and that alpha can be used in the value of E, where alpha is involved. What is that equation here? Yeah, not this. I mean, here is that equation. So once we come up with alpha, we use that alpha in this, use the values of those constants that are involved here, and we will be able to calculate the approximate ground state energy of this anharmonic oscillator under consideration. So with this, I would like to say you goodbye and have a nice time.